In 2017, 8 researchers at Google published a paper called Attention is All You Need. It introduced a new architecture called the transformer, and the key idea was to throw out recurrence and convolutions completely and build the whole thing using only attention. Every major language model since GPT, BERT, Claude, Gemini, they're all transformers. This is the paper that started it. Let's walk through the whole thing. Before the transformer, the best sequence models were recurrent neural networks, RNN chips, and their variants, LSTM chips and GRU chips. They process sequences one step at a time. Word 1 feeds into word 2. Word 2 feeds into word 3, and so on. Each step depends on the last, so you can't parallelize. That's slow, but there's a deeper problem. Information from early words has to survive through every single step to reach later words, and over long sequences, that information just gets diluted and lost. Attention mechanisms helped with this, but they were always added on top of recurrence, so the sequential bottleneck was still there. Now, attention wasn't new. Bottleneck and others had added attention to RNN chips back in 2014, and it helped a lot with translation. But the attention was always a helper sitting on top of a recurrent backbone. Other researchers tried replacing recurrence with convolutions instead. Models like ByteNet and convs2s can compute in parallel, which is faster. But convolutions are local, so connecting distant words still means stacking many layers. This paper asks a different question. What if attention isn't just a helper on top of an RNN? What if it is the entire model? Skip recurrence, skip convolutions, and just let every word attend to every other word directly. That's self-attention. Every position connects to every other position in a single operation, so even words hundreds of steps apart are just one hop away. Here's the full architecture. On the left is the encoder. It reads the input sequence all at once and produces a rich representation of each word in context. On the right is the decoder. It generates the output sequence one token at a time, using the encoder's output to guide it. Both sides are stacks of 6 identical layers. Each encoder layer has 2 sublayers, a multi-head self-attention mechanism and a feed-forward network. The decoder has those same 2 plus a third sublayer that attends to the encoder's output. That's called cross-attention. Around each sublayer, there's a residual connection followed by layer normalization. That means the output of each sublayer is layer norm of x plus sublayer of x. The input skips around the sublayer and gets added back to the output. This helps gradients flow during training, the same trick from ResNet. Every sublayer in the model and the embedding layers too, they all produce vectors of the same size. 512 dimensions. The paper calls this D model equals 512. Keeping the dimension constant everywhere is what makes the residual connections work. You can't add 2 vectors if they're different sizes. So the architecture uses attention instead of recurrence. But how does attention actually work inside the model? Let's trace it with a real sentence. The cat sat on the mat. 6 tokens. Each token starts as an embedding vector, a list of numbers representing that word. In the paper, these vectors have 512 dimensions. For our worked example, we'll use 4 so you can see every number on screen. Each word needs to play 3 roles in attention. It needs to express what information it wants. That's the query. It needs to advertise what it contains. That's the key. And it needs to carry content that other words can collect. That's the value. The model creates these using 3 learned weight matrices, W sub Q, W sub K, and W sub V. You take each word's embedding and multiply it by each of the 3 matrices. For the word cat, its embedding times W sub Q gives you query 2, times W sub K gives key 2, times W sub V gives value 2. Every single word gets its own query, key, and value vector. 6 words means 6 queries, 6 keys, 6 values. Now we have queries, keys, and values for every word. Here's how attention uses them. To find out how much the word cat should attend to every other word, You take cat's query vector and compute its dot product with each word's key vector. A higher dot product means those two words are more relevant to each other. You do this for every pair of words and you get a full grid of raw scores. But these dot products can get large, especially with high-dimensional vectors. Large values push softmax into regions where gradients nearly vanish and learning gets really slow. The paper's fix is to divide every score by the square root of the key dimension. That's why it's called scaled dot product attention. Scale down, then softmax, and you get clean attention weights that sum to 1. The last step is multiplying those attention weights by the value matrix. Each word's output becomes a weighted combination of all the value vectors. Words with higher attention scores contribute more, so cat's new representation pulls heavily from its own value and from Matt's value, because those scored highest. The whole thing happens in one pass, with direct connections between every pair of words. Let's trace the full calculation for all 6 words at once. Stack all the query vectors into a matrix Q, all the keys into K, all the values into V. Each matrix is 6 rows by 4 columns. 6 words, 4 dimensions each. Now, multiply Q by K transpose. That gives us a 6 by 6 matrix of raw attention scores. Each cell is the dot product between one word's query and another word's key. Divide every entry by the square root of 4, which is 2. Then softmax each row separately, turning raw scores into probabilities. Look at row 2 on screen, the row for cat. After softmax, you can see the highest weights land on cat itself and on Matt. The model has figured out these 2 words are closely related in this sentence. The other 4 words get much smaller weights. Finally, multiply this weight matrix by V. Each row of the result is a weighted sum of all the value vectors, using that row's attention weights. Cat's output is dominated by its own value and Matt's value, with small contributions from the other words. That's one complete pass of scaled dot product attention. 6 words in, 6 context-enriched vectors out. Everything we just traced, that's a single attention head. One head can learn one type of relationship between words. Maybe it figures out syntactic dependencies, like which verb goes with which noun. But language has many kinds of relationships happening at the same time, and a single set of Q, K, V projections can only capture one of them. The paper's answer is multi-head attention. Instead of running one attention pass using all 512 dimensions, you split them across 8 parallel heads, 64 dimensions each. 8 times 64 is 512, same total capacity. Each head gets its own completely independent set of W sub Q, W sub K, and W sub V weight matrices. So each head can specialize. One might track adjacent words. Another might link subjects to their verbs across a long sentence. Another might catch pronoun coreference. They all run in parallel, and the total computation cost is roughly the same as one big attention pass, because the per-head dimension is smaller. After all 8 heads compute their attention in parallel, the next step is concatenation. You take the 64-dimension output from head 1, the 64 from head 2, and so on, and stack them into one long vector. 8 heads times 64 dimensions gives you 512 dimensions again. Then there's one more learned weight matrix, W sub O, the output projection. You multiply the concatenated vector by W sub O, and that produces the final multi-head attention output. This matrix lets the model mix information across heads. A syntactic pattern from one head can combine with a semantic pattern from another. So the full formula is concatenate all the heads, then multiply by W sub O. The input to multi-head attention was 512 dimensions. The output is 512 dimensions. Same size in, same size out. That's what makes the residual connections in layer norm work, just like we saw earlier. The transformer uses this multi-head attention mechanism in 3 different places, and each one works slightly differently. First is encoder self-attention. Every input word attends to every other input word, no restrictions. The word mat can directly attend to cat, even though they're 5 positions apart. This is how the encoder builds rich contextual representations. Second is decoder masked self-attention. The decoder generates output one word at a time, left to right. When it's producing word 3, it can only attend to words 1, 2, and 3. It cannot look ahead at words it hasn't generated yet. The model enforces this by setting all the future positions to negative infinity before softmax, which drives those attention weights to 0. Third is cross-attention, where the decoder attends to the encoder's output. The decoder provides the queries, but the keys and values come from the encoder. So, if we're translating English to French and the decoder is deciding what word to produce next, it can attend back to the entire English sentence. It focuses on whichever English words are most relevant to the French word it's generating. So far, we've been focused on attention. That's the first sublayer in each layer. But remember from the architecture overview, there's a second sublayer, a position-wise feed-forward network. Attention lets words exchange information with each other. The feed-forward network lets each word process that information on its own. Same function applied independently to every position. It's 2 linear transformations with a ReLU activation in between. The first one expands the vector from 512 dimensions up to 2048, 4 times wider. ReLU zeroes out any negatives. Then the second transformation compresses back to 512. Each of the 6 layers has its own feed-forward weights, but within one layer, every word position shares the same network. And like every other sublayer, it's wrapped in a residual connection and layer norm. Before any of this processing starts, the model needs a way to turn tokens into vectors. It uses a learned embedding table. Each token in the vocabulary maps to a 512-dimensional vector, and these get learned during training. The paper uses the same embedding matrix in 3 places: encoder input, decoder input, and the final output layer that predicts the next token. What's unusual is the output layer. It takes the decoder's hidden state and scores every token in the vocabulary to predict the next word. Instead of learning a separate matrix for that, the paper reuses the embedding matrix transposed. They also multiply all embedding vectors by the square root of D model, which is about 22.6. Without that scaling, the embeddings would be tiny compared to the positional encodings that get added on top. The transformer has no recurrence and no convolutions. So if you shuffled the words in a sentence, the attention mechanism wouldn't know the difference. Every word would interact with every other word exactly the same way, regardless of order. The model needs a way to know where each word sits in the sequence. The paper's solution is to add a positional encoding to each word's embedding. These encodings use sine and cosine functions at different frequencies. Low dimensions oscillate quickly, changing a lot between adjacent positions. High dimensions oscillate slowly, only varying over long distances. Each position gets a unique pattern across all 512 dimensions. And these aren't learned. They're fixed mathematical functions defined before training even begins. There's an elegant property here for any fixed offset. The encoding at position plus that offset is a linear combination of the encoding at the original position. That means the model can learn to recognize relative distance between words, not just their absolute positions. The paper tested learned positional embeddings too and found nearly identical results, but they shipped the sine wave version because it could potentially generalize to longer sequences than those seen during training. Now we have every component. Let's trace one complete pass through the encoder with our sentence. The cat sat on the mat. Each word starts as a learned embedding vector. The positional encoding gets added, giving the model word order information. These 6 vectors enter the first encoder layer. Inside the layer, multi-head self-attention runs first. All 6 words attend to all 6 words across 8 parallel heads, producing 6 updated vectors. Add the residual connection, apply layer norm. Then the feed-forward network processes each vector independently, expanding to 4 times the width and compressing back. Another residual, another layer norm. That's one complete encoder layer. The output of layer 1 becomes the input to layer 2. Same structure, different learned weights, then layer 3, 4, 5, 6. After the final layer, you have 6 output vectors, 1 per input word. Each one now encodes not just what that word means, but how it relates to every other word in the sentence. These are the representations the decoder's cross-attention will read from. The decoder generates output 1 token at a time. Let's say we're translating our English sentence to French. It starts with just a special start of sequence token. That token passes through masked self-attention, but with only 1 token, there's nothing to mask yet. Then cross-attention reads the encoder's 6 output vectors, then the feed-forward network. After all 6 decoder layers, a linear layer and softmax produce a probability distribution over the full vocabulary. The model picks the highest probability word. Let's say that's LE. Now, LE feeds back in alongside the start token. 2 tokens this time. Masked self-attention lets each one attend only to itself in earlier positions. Cross-attention reads the same encoder output. After 6 layers in softmax, the model picks chat. Step 3. 3 tokens go in, same process, and out comes the next French word. This continues until the model produces an end-of-sequence token. At every step, the decoder can look back at everything it's generated so far and attend to the full encoder output through cross-attention. But it never peeks ahead. Each prediction depends only on what came before. What we just described is inference. The decoder runs 1 step at a time, waiting for each prediction before moving to the next. That's inherently sequential and slow. But during training, we already know the correct output sequence. So instead of generating 1 token at a time, the model receives the entire correct target, shifted 1 position to the right. It tries to predict each token given only the ones before it. This is called teacher forcing. The mask is what keeps this honest. Without it, position 3 could just look ahead and see the answer at position 4. The mask sets all future positions to negative infinity before softmax, exactly like we saw earlier, forcing those weights to 0. So even though every target token is present in the input, each position can only attend to earlier ones. Training gets full parallelism across all positions at once, while the mask preserves the left-to-right constraint. We've covered every component of the transformer. Let's put it all together. On the left, the encoder stack, 6 identical layers, each running multi-head self-attention, followed by a position-wise feed-forward network, both with residual connections and layer norm. On the right, the decoder stack. Same 2 sublayers, but it adds masked self-attention at the bottom to prevent looking ahead, and cross-attention in the middle that reads the encoder output. Embeddings combined with positional encodings feed into both sides. At the top of the decoder, a linear layer and softmax produce a probability distribution over the vocabulary. That's the complete transformer. No recurrence anywhere, no convolution layers. The paper's entire bet is that attention, combined with feed-forward networks and normalization, is all you need. The paper dedicates a full section to justifying this design. Why self-attention over recurrence or convolutions? It compares them on 3 axes. First, total computation per layer. Self-attention costs n squared times d, where n is the sequence length and d is the model dimension. Recurrence costs n times d squared. When n is smaller than d, which at 512 it usually is for typical sentences, self-attention is actually cheaper per layer. Second, sequential operations. How many steps must happen one after another? RNN models process tokens in sequence. O of n steps. Self-attention computes all positions in parallel. O of 1. Third, maximum path length. How far does a signal travel between any 2 tokens? In a recurrent network, it's O of n, 1 step per token in the chain. With convolutions, O of log nil. With self-attention, any token attends to any other token directly. O of 1. Long-range dependencies work because there's no distance to cross. This is the core argument for building an entire architecture around attention. With the architecture justified, the paper moves to how they trained it. 2 translation benchmarks. English to German, 4.5 million sentence pairs from WMT 2014. And English to French, 36 million pairs, one of the largest public translation datasets at the time. Both use byte pair encoding for tokenization. English to German shares a single vocabulary of about 37,000 tokens across both languages. English to French uses separate vocabularies of 32,000 each. One detail worth noting: batches aren't grouped by sentence count. They're sized by total token count, roughly 25,000 source tokens plus 25,000 target tokens per batch. This keeps compute per batch roughly constant regardless of sentence length. They trained on a single machine with 8 NVIDIA P100 GPU cards. The paper describes 2 model configurations. The base model, D model of 512, feed-forward dimension 2048, 8 attention heads, dropout 0.1. It trains for 100,000 steps, taking about 12 hours. The big model scales up. D model 1024, feed-forward 4096, 16 heads, dropout increased to 0.3. 300,000 steps, about 3.5 days on the same hardware, roughly 3 times the parameters, 7 times the training time. And as we'll cite in the results, the big model is the one that sets the new state-of-the-art on both benchmarks. The optimizer is Atom, with beta 1 at 0.9, beta 2 at 0.98, and epsilon at 10 to the -9. But the learning rate schedule is custom. Instead of a fixed rate, they use a formula that increases the rate linearly during a warm-up phase, then decreases it proportionally to 1 over the square root of the step number. The warm-up lasts 4,000 steps. Let's trace the curve. At step 1, the learning rate is near 0. It climbs linearly, and by step 1,000, it's about a quarter of the way to the peak. At step 4,000, the warm-up ends and the rate reaches its maximum. Then the decay kicks in. By step 8,000, it's dropped about 30% from peak. And by step 100,000, it's fallen to roughly a fifth of the maximum. The warm-up prevents instability early on when model weights are essentially random and gradients can be huge. The decay lets the model settle into a good minimum as training converges. 2 regularization techniques. First, dropout, applied at 3 specific points. After each sublayer's output, before it gets added back through the residual connection. On the attention weights themselves, right after softmax. And on the sum of embeddings and positional encodings at the input to both the encoder and decoder. The base model uses a rate of 0.1. The big model increases this to 0.3, but only for the larger English to French task. Second, label smoothing with epsilon 0.1. Instead of training the model to put all its confidence on the correct next token, you spread 10% of the probability mass across all other tokens in the vocabulary. Here's what's interesting. Label smoothing actually hurts perplexity. The model becomes less certain of its top prediction. But it improves BLEU score because softer distributions tend to produce better translations. That's the complete training setup. 2 model sizes on 8 GPU cards. Atom with a warm-up schedule that ramps up over 4,000 steps then decays. Dropout at 3 specific locations, and label smoothing that trades confidence for better translations. Removing recurrence is what makes the training fast. All positions process in parallel, and the mask preserves left to right order without losing that parallelism. 12 hours for the base model, 3.5 days for the big one. Let's see what the numbers actually look like. The main results are in Table 2 of the paper. On English to German, the big transformer scores 28.4 B, LEU. On English to French, 41.0. Both are new state-of-the-art at the time of publication, beating every previous model, including large ensembles. For the BLEU scores they report, they decode with beam search using a beam size of 4 and a length penalty alpha of 0.6. They also average model checkpoints, the last 5 for the base model, the last 20 for the big model. Checkpoint averaging smooths out noise from individual training steps and gives a small but free improvement. What stands out is the cost. The previous best systems on English to French required thousands of GPU hours of training. The big transformer achieves a higher BLEU score at a fraction of that cost. The base model is even cheaper, and it still outperforms most prior systems. Table 3 is the ablation study. The authors take the base model and change one thing at a time to see what matters. Each row answers a specific design question. First, how many attention heads? Dropping to a single head loses nearly a full B. LEU point. But 16 heads also underperforms 8 because when the total dimension budget stays fixed, each head gets less capacity to work with. Second, reducing the key dimension dk hurts, which suggests the dot product comparison needs enough room to make fine distinctions. Third, bigger models just score better. Increasing the dimensions and feed-forward width improves results consistently. Fourth, dropout matters. Removing it drops BLEU by over a point on this dataset. And fifth, the paper test learned positional embeddings instead of the sinusoidal ones. The results are nearly identical, which confirms the choice to ship the fixed version, since it can potentially generalize to longer sequences. The paper includes one more experiment that's easy to overlook. They take the transformer and apply it to English constituency parsing, a completely different task. Parsing means breaking a sentence into its grammatical tree, identifying noun phrases, verb phrases, and how they nest inside each other. With minimal task-specific tuning, the transformer achieves competitive results on the Wall Street Journal benchmark, outperforming several models that were designed specifically for parsing. It doesn't claim to be the best parser. The point is that an architecture built for translation transfers to a structurally different problem without major changes. The self-attention mechanism learns something general about language, not just how to translate. The paper's final figures visualize what individual attention heads actually learn. Remember, each of the 8 heads in a layer can specialize in different patterns. The authors pick specific heads and show where each word directs its attention. Some heads learn syntax. In one example, the attention pattern closely matches the dependency structure of the sentence. Verbs attend to their direct objects. Prepositions attend to the nouns they govern. Another head learns coreference, connecting pronouns back to the nouns they refer to. In a sentence about an animal doing something because it was tired, the pronoun strongly attends back to the word animal. These patterns emerge entirely from the translation objective. Nobody told the model to track syntax or resolve references. It figured out that these relationships help predict the right words in the target language. This paper came out in June 2017. Within 2 years, the transformer had taken over natural language processing. GPT from OpenAI used the decoder half to generate text. BERT from Google used the encoder half for understanding tasks like classification and question answering. Both were direct descendants of this architecture. Then it spread beyond language. Vision Transformer applied self-attention to images by splitting pictures into patches and treating them like tokens. AlphaFold 2 used a modified transformer to predict protein structures, solving a decades-old problem in biology. An architecture designed for translating sentences turned out to be a general-purpose sequence processor. Today, every major language model is a transformer. GPT-4, Claude, Gemini, Llama. All built on the ideas in this paper. The title turned out to be right. Attention really was all you needed. Let's list the key design choices the paper made, because none of them were obvious at the time. Replace recurrence entirely with self-attention, trading sequential processing for full parallelism and direct long-range connections. Scale the dot products by 1 over the square root of dk to keep softmax gradients healthy. Split into 8 heads rather than one large attention, letting different heads specialize. Use fixed sinusoidal positional encodings over learned ones. Share embedding weights across 3 locations. Use a warm-up learning rate schedule to stabilize early training. Apply dropout at 3 precise points and smooth the training labels. The ablation study shows that most of these choices measurably affect performance. This wasn't a lucky combination. Each piece was tested, and the paper shows its work. That's attention is all you need, all 7 sections. We started with why recurrent models were the bottleneck, built the transformer piece by piece, traced the attention mechanism with actual numbers, walked through every training detail, and looked at what the results proved. If you want to go deeper, read the paper yourself. It's only 15 pages, and now that you've seen every concept broken down, the notation should feel a lot more readable. If this was helpful, a like or subscribe goes a long way. Thanks for watching.